What if everything you feel is solid, stable, and obvious about reality is only true from your current point of view? What if time is not universal? What if space is not fixed? What if the universe is stranger than human intuition was ever built to understand? In this video, we will explain Einstein's theory of relativity in simple language, with real science, clear metaphors, and one unsettling conclusion. Reality is far less absolute than it appears. For most of human history, people imagined the universe as a kind of giant stage. Space was the container. Time was the clock hanging above it. Everything happened inside this structure, but the structure itself stayed still. Time passed equally for everyone. Space remained the same for everyone. This was the worldview shaped by Isaac Newton, and for normal life, it works incredibly well. If you throw a stone, drive a car, build a house, or watch an apple fall from a tree, Newton's physics describes the world beautifully. It is practical, it is intuitive, it matches daily experience. But science becomes dangerous to intuition when it starts measuring things too precisely. In the 19th century, physicists began studying light, electricity, and motion more deeply. And slowly, the old picture began to crack. One of the biggest mysteries was light itself. At the time, scientists believed that every wave needed a medium to travel through. Sound needs air. Water waves need water. So light, they assumed, must also move through something. They called this invisible medium the ether. That idea seemed reasonable. If Earth was moving through this ether, then the speed of light should appear slightly different depending on the direction it was measured, just like the feel of air changes depending on how you move through it. So in 1887, two scientists, Albert A. Michelson and Edward Morley, designed a famous experiment to detect Earth's motion through this invisible ether. Their setup was extremely sensitive. If the ether existed, they should have found evidence of it, but they didn't. The result was one of the strangest null results in the history of science. No matter how they measured it, light seemed to move at the same speed. That should not have happened. At the same time, James Clerk Maxwell's equations had already shown that light is an electromagnetic wave, and those equations implied something shocking. In a vacuum, light always travels at the same speed, around 299,792 kilometers per second. So physicists had a problem. How could the speed of light stay constant even when the observer was moving? Then Einstein asked a question that changed everything. What if the speed of light is not the thing that changes? What if space and time are the things that change instead? That was the beginning of special relativity, published in 1905. And once you understand what that means, reality never looks quite the same again. The first big idea is this: there is no universal now. That sounds abstract, but it is one of the most important consequences of relativity. We naturally assume that the present moment is shared across the universe. We imagine that now is a single cosmic slice, the same for everyone, everywhere. Relativity says that is not true. Imagine two lightning bolts striking opposite ends of a train track at the same moment. A person standing exactly in the middle of the platform sees both flashes arrive together and concludes the strikes were simultaneous. But now imagine a second observer sitting inside a fast-moving train, also positioned in the middle relative to the train. If the train is moving toward one flash and away from the other, that observer will receive one flash before the other. So which observer is right? According to relativity, both are. Simultaneity depends on the observer's motion. Two events that are simultaneous in one frame of reference may not be simultaneous in another. That means the universe does not hand out one shared present to everyone. The second big idea is even more disturbing. Time itself is not fixed. According to relativity, moving clocks run slower, not because the machinery is broken, not because the clock is malfunctioning, because time itself changes with motion. This is called time dilation. A simple way to think about it is this. Imagine that reality gives every object a path through space-time. If more of that motion is going through space, less of it is going through time in the same way. The faster you move through space, the more time stretches relative to someone moving differently. At the speeds we live at, this effect is tiny. You do not notice it while walking, driving, or sitting in traffic. But at extremely high speeds, close to the speed of light, the effect becomes dramatic. And this is not just theory. Scientists have tested it with highly accurate atomic clocks. Clocks flown on airplanes have shown measurable differences when compared with clocks left on Earth. Tiny particles called muons, created high in the atmosphere, survive longer than expected when moving at high speed because, from our point of view, their internal time is slowed down. So when relativity says time bends, science answers, yes, and we can measure it. The third big idea is that space changes too. If time is flexible, then distance is flexible as well. An object moving at very high speed becomes shorter in the direction of its motion relative to a stationary observer. This is called length contraction. Again, not because it is being crushed like a soda can, but because space itself is being measured differently depending on motion. This is where relativity becomes deeply uncomfortable for common sense. We like to imagine that length is length, time is time, and reality is just sitting there waiting to be measured. Einstein showed that measurements of space and time depend on the observer's frame of reference. A useful metaphor is a digital map. The city is real. The roads are real. But the way the map displays them depends on scale, position, and movement. The structure exists, but the interface changes according to how you interact with it. Relativity suggests something similar about reality itself. The fourth big idea is that space and time are not separate things. They are part of one deeper structure, spacetime. This was later expressed beautifully in mathematical form by Hermann Minkowski, who showed that the universe is better understood not as 3 dimensions of space plus 1 separate dimension of time, but as one interconnected fabric of events. That word, fabric, gets used a lot and sometimes too casually, but the central idea is real and important. Your life is not just a journey through places, it is a journey through space-time. Every event, every thought, collision, movement, sunrise, decision, and heartbeat has both a location in space and a location in time. The universe is not simply where things are, it is where and when things are. And once space and time become one structure, motion stops being just movement across distance. It becomes a shift in your relationship to time itself. That is an extraordinary idea. Before we go to gravity, there is one famous equation that captures another consequence of relativity, E = mc². This equation means energy and mass are not completely different things. They are 2 forms of the same underlying reality. E stands for energy, m stands for mass, c is the speed of light. And c², the speed of light multiplied by itself, is an enormous number. That is why even a tiny amount of mass can be converted into a huge amount of energy. The important point is not just nuclear bombs or nuclear power. The deeper idea is that matter is, in a sense, condensed energy. Mass is not just stuff. It is energy locked into a stable form. Einstein showed that matter and energy can transform into each other, which completely changed physics. The fifth big idea takes us even further. Gravity is not just a force pulling objects together. This is where Einstein's general relativity enters the picture. In Newton's model, gravity is a force. The Earth pulls on the moon, the sun pulls on the Earth. Objects attract each other across distance. Einstein reframed the whole thing. According to general relativity, massive objects like planets, stars, and black holes curve spacetime itself. Other objects then move along that curved geometry. In other words, gravity is not exactly a mysterious invisible hand pulling things. It is the shape of spacetime. The classic metaphor is a heavy ball placed on a stretched sheet, causing smaller balls to roll toward it. That image is imperfect, but it gives the basic intuition. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. This explains planetary orbits. It explains why light bends around massive objects. It explains black holes, and it explains something even stranger. Gravity changes time too. A clock closer to a massive body runs more slowly than a clock farther away. This is called gravitational time dilation. That means time passes differently depending not only on speed but also on gravity. And once again, this is not philosophical poetry. It is measurable reality. GPS satellites orbiting Earth experience time differently from clocks on the ground. Their systems must be corrected using relativity. Without Einstein's equations, GPS would drift and become inaccurate very quickly. So yes, the map in your phone works better because relativity is real. Now pause for a second and think about what all this really means. If relativity is true, then the world you experience is not the world in some simple, final, absolute sense. It is the world as filtered through your frame of reference. That leads to some profound implications. First, reality is more observer-dependent than it appears. That does not mean truth is fake. It means measurements of time and space are not detached from the observer. The observer is inside the system. Second, human intuition is not built for ultimate truth. It is built for survival. Our brains evolved for medium-sized objects, low speeds, and weak gravitational differences. We did not evolve to feel space-time curvature. We did not evolve to sense time dilation. We evolved to stay alive long enough to reproduce and navigate ordinary Earth conditions. Third, the division between past, present, and future may not be as clean as it feels. Some interpretations of relativity suggest that the universe may be more like a complete structure than a moving spotlight of now. In that view, time may feel like flow from the inside of consciousness, while physics describes something larger and less intuitive. Fourth, perspective is more powerful than the ego wants to admit. Relativity is a physics theory, not a life philosophy. But it does reveal something psychologically important. What feels obvious from one frame may look different from another. Our position inside a system shapes what appears real. And fifth, the most practical implication, our everyday experience may be only a very narrow slice of reality. You feel like you are living inside a stable world of fixed time and fixed space, because at your scale under Earth's gravity, at ordinary speeds, that approximation works. But the universe itself is not obligated to match the version of reality that feels comfortable to the human nervous system. And maybe that is the deepest lesson hidden inside Einstein's work. Relativity did not just update physics. It shattered the assumption that space and time are passive background scenery. It showed that they are dynamic, relational, and woven into the behavior of reality itself. Time is not universal. Space is not fixed. Matter is frozen energy. Gravity is geometry. And the universe is stranger than instinct ever suspected. Maybe the most unsettling part is not that reality is so weird. Maybe the unsettling part is that we are already living inside that weirdness every second of our lives and calling it normal. Lucid order. Question everything.